Good morning, everyone. Can you see the screen share? Okay. So let us get started. So today is the third lecture, and today also it will be kind of a high-level overview of what compilers are and what is the big picture we try to understand in today's class. Starting from next class onwards, we will take a deep dive. Okay. In the next class, we will start with lexical and syntax analysis. But today's class will also be interesting. We will continue with the discussion from the last lecture. So let's get started. So in the last lecture, we started with how emerging computing systems are looking like. Okay. So in this context, let's go here. If you see till early 2000, like for example, till 2005 or so, okay, I'm just checking if I can write on the screen. Just give me a moment, please. Okay, so till like kind of early 2000, like 2005 or so, the way processor manufacturers were giving better performance to the end application users is by coming up with better and better microarchitectures. Okay, so here coming up with better and better microarchitectures means, so they use 2-3 techniques in order to come up with better and better microarchitectures. Number one is by making use of instruction level parallelism, ILP. ILP stands for instruction level parallelism. So that means if there are two instructions, so what this means, what this instruction level parallelism means, if there are two instructions, like for example, one instruction is add R1, R2, R3. The other instruction is another add instruction, let's say add R4, R5, and R6. Let's say there are these two instructions are present in an instruction stream. So let's say the first instruction means add the contents of register R2 and R3 and store it in register R1. And after the processor executes that instruction, the next instruction is add the contents of register R5 and R6 and store it in R4. So if you think about the fetch decode execute paradigm or model of computation that we have, So after you execute, the processor executes the first instruction, then it is supposed to execute the second instruction according to the model of execution that is given to us. But for the sake of performance reasons, if the processor executes these two instructions in parallel, then also the semantics that is given to the programmer is not going to change. So by respecting the semantics that is given to the user, the end user, the processor has the freedom to execute instructions in parallel or even out of order. Like for example, the first instruction is a floating point add. Okay, F-add. Apologies, I'm learning to write using my new device. It's not coming out right, but maybe in a class or two it will get settled down. Like for example, if the first instruction is a floating point add and second instruction is an add instruction, floating point addition takes more clock cycles than regular addition. So floating point add will finish, the second add instruction will finish earlier than the first F-add instruction. So instructions can execute even out of order. So essentially what processor manufacturers were doing is they are trying to exploit this parallelism that is available at the instruction level to execute more computations, to execute more instructions per clock cycle. Okay, this is one method. The second method they use is by reducing the size of the transistors, and they are able to run the processors at a higher clock frequency, improve the clock frequency. It is the second approach. So improve the clock frequency is the second approach. But then the problem is, like as the ILP can keep increasing and clock frequency can keep increasing. But the problem is, in order for the processor to execute instructions at a rapid pace, the memory should be able to supply instructions to the processor at that speed. Okay. But unfortunately, the bandwidth between processor and memory is not increasing at the same pace. So because of that, the processor is not able to realize its full potential. So this is what is called as a memory wall. Sorry, let me erase this. If you have any questions, I will take in a couple of minutes. So this is what we call as memory wall. So because of the memory wall, there is a problem. Okay, the processor manufacturers, they are not able to, although even if you can increase clock frequency, even if you can increase ILP, you can still get into problem. But in any case, you cannot keep on increasing the clock frequency because the power dissipation becomes a problem. Okay, so along with memory wall, we also got power wall because it's not. Let me see. So we have what is called as a power wall. That is the second problem. Okay, and then like the amount of instruction level parallelism that is present in a program, it is not infinite. Like if you think about your programs that you write in C, there will be some independence. Like for example, if you think of a statement such as x is equal to y star 2 plus z star 2, if you translate this expression into equivalent assembly code, maybe you can compute y star 2 and z star 2. The instructions corresponding to these two multiplications you can perform in parallel. But when it comes to addition, you have to wait till y star 2 and z star 2 is computed. Okay. So because of that, the available instruction level parallelism in a program is also limited. Okay. So you hit what is called as an ILPO. So because of these three problems, these are the three issues which processor manufacturers faced from, let's say, early 2000 onwards. But the good thing is still early 2000, so you don't need to the compiler writer. So the change in processor from one generation to another generation, from 1 year to another year, it is minimal, okay? Because not only that, the execution semantics, the execution model that is given to the programmer and to the compiler is the same, okay? So because of that, the compiler writer, so he can work on his algorithms. So what the job of the compiler writer is, so he will, okay. So the job of the compiler writer is he will come up with better optimization passes, better instruction scheduling and register allocation algorithms, so on and so forth. And the architectural model that is given to the compiler writer is not changing. Okay, so the processor manufacturer is doing all the hard work under the hood, but the execution model that is given to the compiler writer is the same. That is fetch, decode, execute execution model. It is the same. And from the algorithm designer perspective, so since the execution model remains the same, so you kind of come up with better algorithms for the problems that you're trying to solve. Okay, like better algorithms for traveling salesman problem. The execution model is the same. Better algorithms for sorting, better algorithms for searching. And it is nice because you are still in that von Neumann execution model. So this is how programmers used to operate. This is how compiler writers used to operate because of the nice abstraction or nice execution model that is given by the processor designer, and the processor designer, he kept working under the hood. Okay. So here in the context of instruction level parallelism, I want to make one note. Most of you may have done compilers, the computer systems organization course. So here there are two kinds of architectures that are possible, okay, to exploit. In your CSO course, you would have studied about what is called as a pipelined parallelism, okay. But pipeline parallelism is it's good, but there are more sophisticated architectures called as superscalar processors, which you wouldn't have studied in your CSO course. You usually study about superscalar processors in a course on in an advanced course on computer architecture. Okay, superscalar, pipeline, and superscalar processors. Okay, let's see if there are any questions. So the class, the Sanjana's question, can the class be recorded? I think the class is automatically being recorded, if I'm right. Yeah, the class is recorded. Yeah, okay. Great, let me. So after 2005, because of these problems, what processor manufacturers started doing is they started shipping out multiple cores on the same processor die, processor chip. So if you look at your laptops now, so they would be dual core processors or quad core processors, etc. So once we have a quad core processor, then the execution model changes because there are multiple threads of execution. Like for example, in core 0, there is one thread of execution. In core 1, there is another thread of execution. In core 2, there is another thread of execution. In core 3, there is another thread of execution. There are 4 threads of execution. So now if you just take your C program that you have written in your programming course and you compile it and run it, it is not it cannot use all these 4 cores unless you explicitly parallelize your program using threads, or compiler automatically does the parallelization for you. Okay. So the important point here is from fetch decode execute model, we moved away from the fetch decode execute model. The fetch decode execute model, it is still there within a core. So fetch decode execute is still there within a core, but outside the core, but there are multiple such fetch decode execute threads going on in parallel. And in order to use these multiple threads available, you have to make use of either the compiler has to do the hard work or the programmer has to do the hard work. So that's number one. This is what we are talking about, thread level parallelism. The second problem, for example, the second issue is each of these cores, they contain what are called as SIMD units. So a SIMD unit is a vector engine. Okay, it has vector instruction set. So for example, if your program has instructions such as A of 1 to 512 is equal to B of 1 to 512 plus C of 1 to 512. So then you are adding two vectors B and C and storing the result in the vector A. So, but usually in C programs, this is not how you write. You write a for loop which iterates from I is equal to 1 to 512, and then you say A of I is equal to, you say A of I is equal to B of I plus C of I. This is how you end up writing in your C program. And where I goes from 1 to 512. This is how you write in your C program. So if you write like this in your C program, then again, you will not be, it's not automatically, you cannot automatically use the SIMD unit. Your compiler has to understand that you are adding two vectors B and C and storing it in another vector A. It has to figure this information out through program analysis. Okay. So this becomes an issue, code vectorization. It's a problem. Either you do the code vectorization by manually, or you rely on the compiler to do it. Number 3 is you know that there are bandwidth issues. Your main memory wall problem is still not solved. So the instructions, in order to, you don't, when you are doing computations, you don't want to go to main memory frequently. So you want to store frequently used instructions within iCache. Like for example, all the instructions that are in a loop, you want to store in iCache, and all the data that you are on which that loop is working on, you may want to store in the D cache or in the L2 cache. So you have to, again, either you write your code to use the memory hierarchy well, or you rely on the compiler to do it for you automatically. And finally, if you see, there is a big challenge you may have written your code, you may have taken a lot of pain in redesigning your code so that you use your memory hierarchy well. But the problem is, let's say this is the last level cache which is shared by all the processors. So what you do is you bring some data into LLC, last level cache, and you want the data and instructions to be present in LLC so that you can, so that when you want them, they are readily available for you. So, but the problem is another thread which is running on another core can come in and displace your instructions and displace the data that you have fetched from the main memory. So you get into a problem of what is called as a cache interference. Okay, so this is a challenging problem, how we can reduce cache interference. Okay, so the point I'm trying to make is the architectures are becoming more and more complex, and we are still writing C programs, we are still writing C++ programs, and the compiler has to put in a lot of effort to see that the program that you have written in C programming language or C++ programming language maps nicely into this underlying complex architectures. Okay, so now the story doesn't end there. So if you go to server machines, okay, server class machines, so on a motherboard, you will have what are called as dual socket motherboards or quad socket motherboards. That is, on the motherboard, you can have 4 different processors or 2 different processors sitting on the motherboard. Okay, so if you see the multi-core processor 1, so it will have some 4 cores. Okay, it may have some 4 cores, and this may also have some 4 cores. Okay, and if it's a quad socket machine, then you will have 4 different processors with 16 cores. And if you, let's say if each of the processors, they are 8 core processors, then you will have 32 core machine. And your memory will no longer be in the size of 16 GB, 32 GB. It can go to 128 GB or 256 GB, etc. In which case, what happens is your memory will be partitioned. So for every core, like for example, this memory module 1, it is local to processor 1. Okay, so here this is local to processor 1. This memory module is local to the processor 1, and this memory module is local to processor 2. Okay, so these are local. So local memory accesses are faster than non-local accesses. This is non-local access. So now when you are writing your program, you want to see that the thread that is running, the program that is running on the processor 1, all the data it requires, you want to place it in this particular memory module. So that way, the memory access time will be smaller. Okay. But what can let's say you put in a lot of effort to see that this happens. But what can happen is the thread that is running here, it could be its time slice is over and the operating system swapped it out and scheduled it out. And when it's scheduled in, it scheduled it on the other processor. Okay, so during after a context switch, so the thread, okay, moved from the thread T1, which is running here, now it is running here on this processor. Now all the memory accesses have now become non-local. So now thread scheduling becomes a problem. Operating system also comes into picture. And when you design algorithms also, you have to worry about what data you want to keep locally, what data you want to keep remotely. So you have to think at algorithmic level, and the compiler has to also needs to understand, no, this thread is accessing this segment of data. So let me allocate memory to this segment of data in this memory module, etc. So the complexity has increased again. So there are few questions. Let me see what these questions are. when we parallelize a loop, the instruction decoding will have in one core. So how it will be shared among its three cores for parallel is cached directly available to the programmer for access. So Prajwal, so the instruction, the execution of an instruction itself will not be distributed across multiple cores. Okay, there will be different instruction streams corresponding to different threads of execution. So an instruction stream corresponding to a thread, it will execute on the core on which the thread is scheduled. So cache is not directly available to the programmer for access, but this is the question from Rishabh, but there are indirect ways to access cache. Okay, but maybe some modern processors permit the cache to be visible to the user in a direct fashion. Okay, but if you look at the processes that are there on your machine, so cache is not directly available. So you have to work with the cache in an indirect fashion. Okay, good question, Rishabh. So Mudit Agarwal has this question: why we don't want to copy the data of T1 from module 1 to module 2 at the time of context switch? It is going to be extremely expensive. Copying data, so you may want to do it if remember, your thread can keep context switching between from one core to another core, or from one processor to another processor. It will be very expensive to copy the data from one memory module to another memory module. Okay, good questions. So yeah, and if you think so the story is over, no? So so along you have on a server class machine, you will have a NUMA system, that is a multi-processor system, and then there will be a graphics processing unit. The architecture of the graphics processing unit is completely different from a multi-core processor, and the programming model is also completely different. So you cannot just write C program and expect it to run on a graphics processor. The compiler really has to do a lot of hard work. In most cases, that is not sufficient enough. What the compiler does is not sufficient enough. So you want to write programs manually by using programming frameworks such as CUDA or OpenCL, for example. Okay. So because the compilers are not powerful enough to completely exploit the underlying graphics processing. Okay. And in more complex servers, like for example, you can have a NUMA system, that is a multiprocessor system. You can have multiple GPUs. Okay, so you have one GPU here, another GPU here, and then you can have a tensor processing unit or a deep neural network accelerator. Okay, so DNN accelerator, CNN or DNN accelerators you can have. And then you can have an attached FPGA, which is on which you can design your own hardware architectures or hardware accelerators and flash it on the FPGA. So if you take a system, the underlying complexity of the system is exponentially blowing up. Okay. So the challenge is from single core von Neumann computing structure. So this is what single core computing structure. This is from sequential model of computation, we move to extremely complex architectures. Okay, and programming GPUs or programming FPGAs or TPUs. The way we think about algorithms, the way we think about these architectures is very different. Okay. So the challenge here is, if this is your whole programs, okay, some part of the program might be good for CPU and some part of the program might be good for GPU. and some part of the program might be good for TPU. Okay, and some part of the program, no, like you may want to have you may want to use your FPGA. So how do you figure out, given a program, which part is good for what? Okay, so manually checking is hard. Okay, that's what it is being done right now, and you want to rely on compilers, but for compilers also it's extremely hard because your source programs, they are written in a sequential model, assuming a sequential model of computation, but the underlying architectures are way different from the sequential models of computation. So it's a big challenge for the compiler. Okay. And if you think the story ends there, it's not the case, because if you take a data center, so you will have a huge collection of nodes, like, okay, 100 machines, 1,000 machines, etc., or 10,000 machines if you think of Amazon or Google scale data centers. And each of these machines, they have different kinds of configurations. Okay, and they are connected through some high-speed InfiniBand network. Okay, and they have some local storage. Okay, this is the local storage, and there is also some remote storage. Okay, so there is also some remote storage, and there is a high-speed connection between these nodes to this remote storage through what is called as a storage area network. So given a computational task, so how do you use your this collection of machines so that you can get your job done? Okay, like for example, those of you, like these days AI/ML applications are very popular. Okay, uh, so if you want to train a deep neural network, okay, a convolutional neural network, CNN or RNN, if you want to do, see, these models are so big, so they don't even fit into one machine, or even if they fit into one machine, you want to use the computational power that is available across nodes so that you can do your training fast. So given a CNN training algorithm or an RNN training algorithm, how do we map that training algorithm through this to this heterogeneous collection of nodes? Okay, so this is the grand challenge that we have. In order to solve these problems, different computational program frameworks are proposed. Like for example, in your operating systems course, you may have read about pthreads. Okay, it's to do multi-core programming. OpenMP is another programming model. It's another computational framework for again using multi-core machines. Okay, and if you see, like for example, these two, they are useful for multi-core machines. And then like for example, OpenCL, CUDA, OpenACC, they could be useful for programming GPUs. Okay, and then if you think about remote procedure calls, message passing API, Spark, Regal, all these things, these are all distributed computing frameworks. Distributed computing. So in a complex application, you may end up using, some code base could be using pthread, some code base could be using OpenMP. And then in order to use GPUs, you may want to use CUDA, and then you may want to use MPI or remote procedure calls. So yeah, so you may want to use a mixture of these computational frameworks in order to get best performance for your application. So the problem statement that we have is there's a problem specification. An example of a problem specification is, let's say, CNN training, okay, convolutional neural networks training. This is the problem. And this training algorithm is there with you, and you want to come up with an optimal orchestration strategy. Okay. So what is an orchestration strategy? As I said, if this is the whole program, you want to split this program and want to say, this chunk of the code runs in one node N1, and this chunk of the code runs in node N2, and this chunk of the code can run in node N3. And within node N1, if you take node N1, okay, you may say, this part of the code, you use a CPU in some particular fashion, you use GPU in some other particular fashion, and then you may also want to use TPU, okay? And the way you want to use the CPU, that CPU, again, if you think about it, it has multiple cores. So there is core 0, core 1, core 2, core 3, and then you want to see whether you want to use whether 4 threads you want to use, or you want to use 8 threads for execution. Okay, and if it is a GPU, what is the launch configuration? What are the grid dimensions? So those of you who know about GPU programming, so we may want to worry about, you'll appreciate, what grid dimensions means. So you have to figure out how do you want to split the problem, and for each of the architectures, how many threads you want to use, and what kind of tiling strategy you may want to use, like for example, to enhance memory locality. So it's a complex optimization problem. Okay, and the ideal thing and what we expect is we continue to write our programs in C, C++, Python, and we hope that there's a magic compiler which does all this orchestration job for us. Okay. So there are, this is, now we enter into what is called as a design space explosion problem. That is, there are exponentially many ways of mapping your program to underlying architecture. Okay. So that is, there are exponentially many program orchestration strategies. So finding an optimal orchestration strategy for your program is close to impossible. Okay, finding even a near optimal orchestration strategy is equivalent to finding a needle in the haystack. Okay, so this is the biggest problem. Okay, so finding an optimal orchestration strategy. Okay, so this is a very challenging problem. And this is where a lot of research in compilers is happening now. Okay, so one specific area of research which we work in computer systems group is how we can use machine learning techniques. So the question here is, can we use machine learning techniques to build performance prediction models okay, and these performance prediction models can aid the programmer can not the programmer can they can help us in checking out, like for example, if this is the space of orchestration strategies, using the machine learning model, we can say, these are not good orchestration strategies, or we can say, and these are moderately good orchestration strategies. Okay, and so these are really good program mapping strategies. And then if you can narrow down to few important program orchestration strategies, then we can actually run our program using these orchestration strategies and pick the best one. Okay, if you want to map our program in different ways and run our program in all possible ways, it is not going to happen. It's an extremely expensive job. Okay, so now we move to the, let me take a moment here before I move to the next part of today's lecture. Let me see if there are any questions. If cache can be accessed indirectly, how exactly it is done? Any example? Okay. So Tushar, I will give you a good question. I will give you one example problem. Okay. And homework you can work on. So it gives you some idea on how we can use cache in a indirect fashion. Good question. If there are any other questions, please ask me now. So before I move to the next idea. All right. It seems you're all doing good. So let me go ahead. So the next idea is on interpreters and virtual machines. Okay. So in C programs, so you have the what do you do? So if you want to execute your C program, you say gcc hello.c and then you say dot slash a dot dot. This is how you execute your C program. But then let's say if you have written a Python program, so what do? You simply say Python, okay, maybe hello.py. There is no compilation step here. So here there is a compilation step, but here there is no compilation step. Okay. So your Python program without translating it doesn't translate your code into target machine code, it interprets it directly. So these are called as interpreters, and these languages are called as interpreted languages. Like for example, yeah, in your UG1 or in some IT workshop course, you may have learned shell programming. In shell programming also, your bash shell interprets the shell script. Okay, there is no translation of your shell script code into machine code. Okay. Similarly, Perl is also an interpreted language and JavaScript is also an interpreted language. So there is no compilation step, explicit compilation step involved, and your program is directly interpreted by the interpreter, by the corresponding language interpreter. There is no code translation happening. In this course, we will not study much about interpreters, but the ideas that you learn in designing compilers, they are very well applicable to interpreters. Okay, so for example, if you, almost all interpreters, if I'm right, they translate the source program, okay, into an intermediate representation, And this intermediate representation could be like abstract syntax tree representation or bytecode representation, etc. So in this course, you will understand what these abstract syntax trees are and how you can represent a source program in the form of abstract syntax tree. Once you represent your source program in the abstract syntax tree form, it is possible for you to interpret your abstract syntax tree, or you can map your abstract syntax tree into equivalent machine code. Okay. So the theory that you learn, the engineering principles that you learn in this course, they are applicable even for even if you want to design interpreters. Okay. So just to give an idea about what this AST to quickly, like for example, if you have an expression such as x is equal to y plus 2, then you can represent this expression as x is equal to in this tree form. Okay. Then once you represent this expression, this assignment statement in this tree form, you can interpret this. You can interpret this tree by traversing this tree or evaluating this tree by doing a postfix traversal. Okay. So you visit left node, evaluate the left subtree, evaluate the right subtree, and then you do the computation at the node. Okay. And you repeat this process. So this is a simple example of an interpretation. Okay. Let's say Java programming language. Okay. Let's now take Java programming language. The Java programming language, so what it does is when you write your program in Java, so it translates it into an intermediate form called as bytecode. Okay. And this bytecode is interpreted by the Java virtual machine. Okay. And if I'm right, the Java virtual machine, it is what is called as a stack machine, or it is a stack architecture. Okay, it's not that important for us. But the important point that I want to understand is that Java program, it gets translated, the Java compiler, there is a Java compiler. The compiler doesn't translate the program into native code, but it translates into an intermediate form called as bytecode. And this bytecode is given to the Java virtual machine, and the Java virtual machine interprets that bytecode and generates a suitable output. So here, a couple of things we would like to mention. The advantage with interpreters is if you have, like for example, hello.py, if you have written hello.py code, and if you share this hello.py code to your friend, okay, so this machine, this script successfully runs on your machine, and this is your machine. Let's call it as M1. And you send it to your friend who has different machine, M2, and with high probability, he will be able to execute your hello.py code. Or there is a bytecode file which is generated, Java bytecode file, and that bytecode file is transferred to the other machine, and that by the virtual machine on that on the other machine can interpret that bytecode. In fact, the origin of the Java programming language is in the context of web, where there are programs which you would like to run on your web browser. So if the programs are compiled it into native code, then different machines across the world will have different architectures. So if you have compiled your code into, let's say, x86-64 instruction set architecture, and if it is transferred to a machine with ARM instruction set architecture, it cannot execute. So instead, you write your programs in Java, and they will be translated into bytecode and all the machines across internet. So let's say these are all different machines on internet. So all of them, they will have JVMs on it, Java virtual machines, okay? And all these JVMs, they understand, and you are here, okay? So you are here, okay? So you translate, you send your bytecode, okay, to all these machines, okay? Or they want to use your application, they get the bytecode of your application, and the Java virtual machine on their machine can execute it. But if it is, if your application is x86-64, then if you send it across to a machine which uses ARM instruction set architecture, then you are in trouble. So the origin of this Java programming language is when the internet emerged. They want to find a IR or a representation of a program which is instruction set architecture neutral. Okay. So this is one, portability. So interpreters help in portability. So big advantage of interpreters is code portability. Code portability is a big advantage. But there is a problem you can see if you have a statement such as x is equal to y plus 2 in an instruction set architecture. This can simply turn out to be add I register R1, R2, that is add immediate constant 2 to register R2. Register R2 corresponds to variable y, and register R1, it corresponds to variable x. So this instruction, add I instruction, it takes less than one clock cycle to execute. But on the contrary, if you take, if you want to make a postfix pass, if you want to do a tree traversal of this AST tree, then you have to execute hundreds of instructions. Not only that, you have to access, you have to make hundreds of memory accesses. Okay, so performance becomes a problem. Big problem is performance. Okay, this is performance becomes a problem. Okay. So I really hope that you appreciate the fact that this x is equal to y plus 2 when it is executed in native code. This is what native code. It takes less than one clock cycle. But if you want to interpret it by constructing a AST tree, then the number of instructions that you have to execute are multiple, because you have to do a tree traversal, which itself induces many main memory accesses. But whereas if you look at this add a instruction, there is no main memory access at all, except for the instruction fetch. But whereas here you have to do many main memory accesses, and you have to do this tree traversal, so on and so forth, because it turns out to be very expensive. So while interpreters are good for portability, they are bad when it comes to performance. So this is the issue. Okay. So this is what we discussed before. And as I said, the focus of this course is on compilers, but the ideas that you learn in designing compilers, they are very well applicable to interpreters. So in order to solve this performance problem, the virtual, there is what is called as, there are what are called as hotspot compilation techniques. Okay, so what happens is your Java program, it is translated into bytecode by a Java compiler, and this bytecode is given to the virtual machine. So now, so we have what are called as hotspot virtual machines. What these hotspot virtual machines will do is, they check as they execute the program in the bytecode, they check what are the frequently called methods, and methods containing loops that loop a lot. Okay, so these code, they will be translated into native code at runtime. As your Java virtual machine is interpreting your bytecode, it identifies the hotspots. Like for example, if this is your whole bytecode program, and let's say this is a segment of the code which is a hotspot. This is a hotspot. So the program, the virtual machine, dynamically translates this into native code. And once it gets translated into native code, then the execution, there will be a performance boost that your program gets. Okay, like for example, in this code, if you see, this is the main function, and in this main function, this is a loop, and this is for large values of a, this loop turns out to be a hotspot. And since this loop is a hotspot, the function call that it is making, square sum, it also becomes a hotspot. Okay. So if you compile this, if you run this program in a pure interpretation mode for when A is set to 10 million, okay, it takes 0.37 seconds to execute. But whereas if I enable hotspotting, JIT stands for JIT means just in time compilation. Just in time compilation. Hotspotting, JIT. So there are three terms we use: hotspot compilation, okay, dynamic compilation, and JIT, just in time compilation. So all these are very synonymous. Okay, by using this hotspotting approach, we are able to reduce the time from 0.37 execution time from 0.37 seconds to 0.07 seconds. I just asked a question here, any other details missing, because I have to specify what is the processor on which this program has run, because these numbers, that 0.37 seconds or the performance boost that you got, etc., it is very much dependent on the processor, amount of memory you have, and other things. So if you take the same program and run it for the same value of A, each of you may get a different kind of performance boost. Okay, so don't expect the same boost. And I did this experiment 5-6 years back on one particular machine that I have. I don't even remember what configuration that machine has. Okay. So with this, I will break for, I'll stop today's lecture. In the next lecture, we will start taking a deep dive into uh, into the design of compilers, that is actual theory. This is all high-level overview. In particular, we will study syntax analysis, lexical and syntax analysis in the next class. In fact, I will try to give a demo, some kind of a tutorial on a particular tool so that you can get started on your project. And I want to see if you have any questions. So when compiling, Gaurav Chaudhary has this question. While compiling, we go through the entire source code unlike interpreters. So can we say parallelism can be better exploited in languages that compile and execute, or there is no such relation? Well, actually, even in interpretation also, the program in some sense, it goes through, it constructs a complete AST representation of the source code. So even interpreters have access to the whole source code. So interpreters can also get better parallelism, just not compilers. So Anurag Jain has this question: if compatibility is an issue, then why not compile from source before running? Well, this is what we try to do when we try to install applications, like, when we try to download something from the web, we compile it. This kind of works all right for some applications you want to install, but let's think of a website, web page, which uses some kind of program that is running within web browser. Uh, then in that case, downloading it, compiling it, running it, it's not the same experience. Because if you see many websites that we use, or all, pretty much all the websites that you see now, they are designed using JavaScript, okay? And JavaScript is an interpreted language. So because of that, independent of what machine you have, you simply access the web page and everything works for you. But if you have to download it, compile it, and then execute it, the experience will not be the same. Karthik Gupta has this question: in JIT, we are recompiling during runtime. Doesn't that have a significant overhead? Very good question, Karthik. So it depends. So the compilation effort, the execution time benefit should outweigh the compilation effort that we put in during runtime. Okay, so let's say, so if you are very aggressive in just-in-time compilation, you will actually impact the program performance. So you have to be, the compiler will be careful in deciding what are the hotspots and which are worth the compiling into native code. How does, Funny Ritvich has this question: how does processor determine that ILP is possible at some point of time without doing additional comparisons? Good question, Funny. You need to take a complete course on computer architecture to answer this question, but there are very nice techniques to achieve this, to do that. Yes, Shaurashya has this question: how is Java interpreter different from C's assembler, especially if the assembly codes are the same for two C compilers on different machines? Well, C's assembler, it is very tied to a instruction set architecture, right? So there is nothing like C's assembler, okay? So there's an assembler for an instruction set architecture. So it's, yeah, so there's no comparison, yes, actually there. Okay, because bytecode is not tied to any instruction set architecture. So, but whereas the assembler or assembly is tied to an instruction set architecture. Okay, so time is up. So let's we will regroup in the next class. Again, I hope you're all doing well and you're enjoying the course. As I said, we are going a bit slow for the first 3 lectures, but we will pick up pace from next lecture onwards. Okay. If there is any feedback that you would like to give me in terms of improving the class, please feel free to drop an email so that I will make suitable changes in the way I deliver the lecture. So how can we access recordings here? So Nishant, I will get a link from Zoom link, which I'll share with you. Or actually, yeah, so don't worry, by the end of today, I will send an email with a link to the recording of this Zoom lecture. It is available on cloud and you will get it. Okay. All right then. So that's all for today. Have a great day, guys. Bye. Thank you. Namaste. If anyone have questions, if you want to stay back and ask, I'm happy to answer your questions.